Okay, so here in this video, we're going to look at like various equations using stoichiometry. So along the way, we're going to be making use of a lot of the skills and thinking and formulas that are central to like being able to answer these successfully. Okay, so we can start off with, I think we'll skip question 6. We'll just look at question 7 here. Nitrogen in the cylinder of a car reacts with oxygen in the equation that we see here. So I'll snip this, bring it down. Okay. All right. So here, this question here is asking us firstly, how many moles of nitrogen are needed to produce 1.52 moles of another substance, nitrogen monoxide, and then how many grams of oxygen are needed for this reaction. So what are they saying? They are saying that they want us to, they've given us, in terms of number of moles of nitrogen monoxide, 1.52 moles is what we need, okay? And they're asking us to work out how many moles of nitrogen we need to produce this many moles of nitrogen monoxide, okay? So stoichiometry, one of the ideas behind stoichiometry is that when you have a chemical equation like this, which shows us like the ratio in which all the substances react, okay? You see here that 1 molecule of nitrogen reacts with 1 molecule of oxygen to produce 2 molecules of nitrogen monoxide. And so the thing with moles is that you can substitute the words molecules and atoms, ions, particles for moles. So we said here 1 molecule of nitrogen reacts with 1 molecule of oxygen to produce 2 molecules of nitrogen monoxide. You could say 1 mole of nitrogen reacts with 1 mole of oxygen to produce 2 moles of nitrogen monoxide. Okay, so like 1 mole to 1 mole, okay, in the reactants produces 2 moles of product. And this here forms the basis of our ratioing later on. So like if we need to find out how many moles of nitrogen monoxide, how many moles of nitrogen we need to produce 1.52 moles of nitrogen monoxide, what we do is we set up some kind of ratio. The easiest way to do this is set up a fraction. So we want to find out number of moles of nitrogen, so this goes there, over number of moles of nitrogen monoxide. And then we establish this as the molar ratio. The mole ratio, so nitrogen here is in a 1 to 2 mole ratio. In other words, 1 molecule of nitrogen can lead to the production of 2 moles of nitrogen monoxide. So this is a 1 to 2 ratio there. So I prefer to put this in a fraction straight away rather than to write out a ratio like this. This is fine too. So the ratio of number of moles of nitrogen to monoxide is 1 to 2. And then you can turn these into fractions. Okay, so then we'll get rid of the colons and make that a fraction too. And that's fine as well. But I like to just like set it up so number of moles of nitrogen over number of moles of what you have over the what you want to find, in this case nitrogen, over number of moles of what you have, in this case nitrogen monoxide, is equivalent to 1 over 2, the coefficients here, 1 to 2, okay? And then we know what this value is because we have it over here, okay? We just sub that in. So number of moles of nitrogen is 1 over 1.52 equals 1.5. Some of you might, and I prefer this, you might just rearrange this first before subbing in your values, okay? That's fine as well. And so that's the number of moles of nitrogen that is needed to produce number of moles, to produce 1.52 moles of nitrogen monoxide. Now they're asking how many grams of oxygen are needed for this reaction. Now to work out what they're asking us essentially is to find this. Now to find this, we need to first find this, okay? so that we can then use the N equals M on capital MR rearranged, which is this one here, to find the mass, okay? So we can either work from the number of moles of nitrogen monoxide that we want to produce, or we can work from the number of moles of nitrogen that we need. And I would just go from the nitrogen, because the ratio of the oxygen that is required to the nitrogen that's required is 1 to 1. So if you see here, 1 mole of nitrogen reacts with 1 mole of oxygen. So they react in equal molar ratios. So you could say number of moles of oxygen equals number of moles of nitrogen, because they react in exactly the same amount in moles, okay? Very easy to do this when you see that the coefficients in the chemical equation are the same. So the coefficients, that is like these numbers at the front, are 1 for both of them. So they have the same equivalency in terms of mole reactivity. And then now we can work out the mass of oxygen by using that equation. So number of moles of oxygen multiplied by molar mass of oxygen. So we have a 0.76 mole times by 32 grams per mole. So 32 grams. So 1 atom of oxygen is 16 grams per mole. We have 2. So that's what we've got. So 23.04 grams. Or just 23 grams. Okay, so we need 23 grams if we're going to do the correct sig figs. 23.0, 0.760, 3 significant figures. Okay. So that there is a very, very standard stoichiometric question. And we have a bit of everything. So we have, of course, like the main feature is setting up a ratio like this and being able to work out the number of moles of a certain substance by setting up this ratio. And it's very likely that you'll have to use this equation in some form and rearrange it. Okay? Key equation. So let's pick another one. Let's pick something with big numbers. So here we have cellular respiration. We break down a glucose with oxygen to produce carbon dioxide and water. Fantastic reaction. And okay, so glucose, C6H12O6. Now we have 8.9 grams of glucose. 8.9 grams of glucose, and we need to determine the mass of oxygen needed to react with that amount of glucose. Now we can't just multiply that mass by 6 to get the mass of oxygen, okay? We can't just multiply the mass of glucose by 6. We have to work out first the number of moles. Then we can stoichiometrically ratio the amount of oxygen, the number of moles of oxygen with the number of moles of glucose. So we work out the number of moles of glucose first. Always be trying to work with moles for these questions that involve stoichiometry is the key point here. So we use this equation again. Okay, so that's going to be 8.9 grams divided by 180 grams per mole. So you have to work out the molar mass of C6H12O6. Luckily, I just happen to know that's 180 because I see it all the time. But if I would do this on the side if you for pretty much any substance that you don't know the molar mass for. So it'd be 6 times 12 for carbon plus 12 times 1 for hydrogen plus 6 times 16 for oxygen, and that should be 180, okay? And that's what goes here at the bottom. Okay, so it goes here. We plug that in. 8.9, clear. 8.9 divided by 180. 0.0494 moles. Okay, so now we have the moles of glucose, but we want to find the mass of oxygen required. So we need to find the moles of oxygen first. Now, number of moles of oxygen ratioed against the number of moles of glucose. How do we do this? We look at the chemical equation to find out the stoichiometric ratio. So you look here that glucose has no coefficient in front of it, so it's got a 1 essentially. So 1 molecule of glucose reacts with 6 molecules of oxygen. You can substitute the word molecules for moles. 1 mole of glucose reacts with 6 moles of oxygen. So you could say then so for every 6 moles of oxygen, so number of moles of oxygen, 6 is here. You just put the coefficient in front of oxygen. 1 mole of glucose is needed. So 6-to-1 ratio right there. So you try to set one up logically. Set one of these ratios up logically, and then you can rearrange it. So number of moles of oxygen is 6 times the number of moles of glucose. So 6 times 0.0494 moles. What's that? Calculator. 6 times answer. 0.297 moles. And now we need to do the last step. They want us to find the mass of oxygen. So mass is number of moles of oxygen multiplied by oxygen's molar mass, which is 32. So 0.297 times 32 grams per mole. Note how I'm writing all the units out. It can be really messy writing all the units out within your calculations, but it is essential that you write out the units for your final answers. So when you get to the end of a calculation like I am here, so I've worked out the final value of the mass of oxygen, you must show the unit at the very end. Okay, or even like, when you work out these final, the final values for each of these other things, like number of moles of oxygen, for example, here, or number of moles of glucose, you must put in the units. It's essential, okay? Really bad form if you do not, and I imagine some examiners will deduct marks. They'll also deduct marks if you don't show this kind of denotation, that you're showing your what you're working out for in every step. So I'm here showing very clearly that I'm working out number of moles of oxygen. Then I show very clearly I'm working out mass of oxygen. And this is how you write it, okay? Textbooks will do them similarly, and good revision books will do them similarly. And the reason why they do it similarly is because there's a standard way of doing this. This is the standard, proper way of doing it, doing these calculations, okay? So practice this. What do you need? All right, so let's just do another one with a little bit trickier of a ratio. So, yes, I was thinking 16. Okay, so 16. Let's go with 16 here. Oh, I didn't do the second part of that question. That's okay, I'll leave that. I think it's very similar in process, okay? Let's do 16. All right, so we want to find the mass of aluminium oxide produced, okay? We know that 5 grams of aluminium was used. So, standard procedure, convert stuff to moles. Convert what we have to moles. Number of moles of aluminium is mass of aluminium over molar mass of aluminium. I think aluminium weighs 27 grams per mole. Yep, so aluminium here, 26.982, 27. Whoa, my grams per mole. So 5 by 27. 0.185 mole. Okay? So we want to work out the number of moles of aluminium oxide, Al2O3, before we can work out its mass. So we need to use the stoichiometric ratio. So you look here at the equation. You get 2 moles of aluminium oxide for 4 moles of aluminium. So if you set up this ratio there, every 2 molecules of aluminium oxide needs 4 molecules of aluminium. Oh, sorry, 4 atoms of aluminium. I say the word molecules. No, aluminium oxide, you know, isn't a molecule, but so molecules in air quotes. So number of moles of aluminium oxide then is half times number of moles of aluminium. Okay, so we have that somewhere, just up here, 0.185 mole. So we divide that by 2, 0.0926 mole. Now we can work out the mass of aluminium oxide. So mass of Al2O3 is number of moles of Al2O3. So this is the N equals M on capital MR equation that we've rearranged. So the number of moles of Al2O3 is 27 times 2, so that's for aluminium, plus 16 times 3. So I need to work that out. 27 times 2 plus 16 times 3. 102. 102 grams per mole. So we go 0.0926 mole, that's the number of mole of aluminium oxide that we have, times 102 grams per mole. Back to the calculator. So I need this. How do I get you back? Oh, I don't know how to do that, so I can just... Surely there's a way to reuse an answer from previous, huh? I guess not. So usually what I do with my scientific calculator when I want exact values, I just do everything again, you know, and like doesn't usually take too long if you know what you're doing. I don't really know what I'm doing. Not with this calculator. See, I've very stuffed it up. I've lost it again. 554, you say?
5/54.
Oh, that's a good idea. That's a good idea. That is a good idea. Anyway, so we're here. Answer times 102. There, 9.4 grams. So 9.4 grams of aluminium oxide. 2 significant figures, okay? Because we only have here 2 significant figures. So 9.4 grams. Okay. Again, key things. Showing what you're calculating for, including units, okay? Showing what you're calculating for, using units. Setting up these molar ratios very carefully here. Yeah. One thing that I was doing in this question that I didn't do previously was I listed out what I wanted to find and what information I had already. That's a good thing to do as well. Not essential, but it helps with like developing a plan on what to do, yeah? Helps. All right. Hopefully it's starting to click for some of you, or it's coming back if like, you know, you're seasoned veterans and you've kind of gotten... okay, here we go. This is this question here. This question here will need some work. I'm just interested in the calculation, not in the diagram. You're welcome to work through the question with the diagram or whatever, but I just want the question. Now this question here is interesting because they want us to work out how much of something is produced from 100 tons. And that's not in grams, okay? We only can really work with grams. And also they give us a percentage for one of the substances. Okay, so limestone, which is a raw material, is not pure calcium carbonate, but a portion of the limestone, exactly 83.5%, is what reacts in this equation here. So how does this factor in? So if we know that 83.5% of the limestone is calcium carbonate, then in 100 tons, okay, we will have, so if you multiply, so the mass of calcium carbonate is 83.5% times 100 ton, okay? So that would be 83.5 ton. So you could turn this percent into 83.5 over 100. So we get 83.5 ton. So I've just written T for ton. Now we've got to turn it into grams. So a ton is 1,000 kilograms. 1,000 kilograms is 1,000,000 grams. So 1 million is, to make it scientific notation, is 10 to the 6. Okay, so we can just turn 83.5 T into 10 to the 6 grams. So remember, going from a ton to kg this is 10 to the 3, and to grams 10 to the 3. You multiply 10 to the 3 with 10 to the 3, you get 10 to the 6. So those two different unit changes gets us this 10 to the 6 multiplier. So we've got a mass of calcium carbonate. It is huge. We want to work out the mass of quicklime. So quicklime is CaO that's produced. Okay, now to work that out, we've got to work out number of moles of calcium carbonate. Mass of calcium carbonate over molar mass of calcium carbonate. I don't know what the molar mass of calcium carbonate is, so I've got to work it out. I'm not given it either. My screen's being weird today. Molar mass of calcium carbonate equals, what's calcium? 40.1 plus 12 plus 16 times 3. So we plug that in. 40.1 plus 12 plus 16 times 3, or 48. 100.1 grams per mole. So that goes into here. So 83.5 times 10 to the 6 grams, that's calcium carbonate in grams, over, yeah, my screen is really weird, 100.1 grams per mole. So I'll just go 83.5 times 10 to the 6. Oh, nope. How do I go down? So again, like, know how to use your calculators, yeah? Don't be me. Go away. What is this thing? No, I just need to go down again. Times, hang on, sorry, times 100.1. Oh, syntax. Oh, hang on, yeah. I don't know how to get rid of that though. Backspace. I'll bring up this keyboard. Nice. Good solution. So it's 8.36. 8.36 times what? Oh, did I? Oh. Okay. Thank you. Oh. You guys have gotten this down pat. Yeah, I gotcha. Okay. We do this. Answer. Boom. Okay. 8.34 times 10 to the 5. Wait, was it 3, 4 or 3? Yeah, 3, 4. So moral of all of this faffing around, make sure you know how to use your calculators. So I usually have a nice like scientific calculator. I just want you to be able to see all the calculator work. That's a bit of a waste of time. Okay, so I think from those 4 questions that we've done, we have touched on like pretty much all the major skills that are involved with mass stoichiometry. So when we convert from the mass of one substance to the mass of another substance within a chemical reaction, okay? So we need to convert to moles, okay? I'll summarize this process, okay? If you have the mass of something, you have a mass of a known substance. You need to turn it into the number of moles of a known substance, so that then you can work out the number of moles of the unknown substance, like the substance that you don't have the mass for, okay? And then you can work out the mass of the unknown. This is like the key thing. So to go from, that being said, like going from number of moles of the known to the unknown, you need to use stoichiometry. You're using that ratio stuff, okay? That's when you're looking at the chemical equation. Alrighty.